Imagine a world encircled by a halo of ice and dust, a giant globe of gas spinning in the cold, dark expanse of space. This is Saturn. For most of human history, it was just a wandering star, a faint point of light. Even through early telescopes, it was a marvel. A planet with strange ears we later understood to be a magnificent system of rings. It floated in our imagination, a symbol of distance and mystery. We yearned to go there, to see it not as a speck, but as a world. We wanted to send our emissaries, our robotic explorers, to bridge the vast ocean of space and report back. The journey would be long. It would take years, billions of kilometers from Earth. The technology had to be perfect. It had to survive harsh radiation and the cold vacuum. The machines had to be more than travelers. They had to be our eyes, our ears, and our hands. They would carry cameras to show sights no human had seen. They would carry instruments to taste the air, to measure unseen forces, and to map hidden landscapes. This endeavor began not with a leap, but with a first tentative step. Our journey to Saturn is a story of human curiosity, from a fuzzy blob in a telescope to geysers of water erupting from an icy moon. Each mission a chapter, building on the last. We started with a simple flyby, a quick hello, then more sophisticated explorers for a closer look. Finally, a dedicated resident, a satellite that made Saturn home for over a decade. The saga transformed Saturn into a complex system of worlds. Before we could run, we had to walk. The first missions tested the waters. Could a spacecraft survive the journey? What dangers lurked around Saturn? The asteroid belt had to be crossed. Intense radiation belts had to be navigated. These early missions were scouts, mapping hazards. They were pioneers, paving the way. Their courage and findings laid the foundation for what we know today. The first robotic emissary to reach Saturn was Pioneer 11, launched on April 6, 1973. Its primary mission was to Jupiter, but it was given a second life. After its successful Jupiter encounter, NASA engineers guided it onto a new path, one that would take it across the solar system to Saturn. On September 1, 1979, after a journey of more than 6 years, Pioneer 11 made its historic flyby. It passed just 21,000 kilometers above Saturn's cloud tops, a daringly close approach. For the first time, we saw the ringed planet not as a distant point of light, but as a destination. Pioneer 11 was a relatively simple machine by today's standards, but it was a marvel of its time. It carried instruments to measure the environment around Saturn. Its photopolarimeter was not a camera in the modern sense. It measured the intensity and polarization of light to build up images, strip by strip. These were the first ever close-up pictures of Saturn. They were grainy and low resolution, yet they were revolutionary. They revealed details never before seen from Earth, including a new, faint ring, which we named the F-ring. The spacecraft's data showed this ring was a narrow, intricate structure, hinting at complex forces at play. Beyond the images, Pioneer 11 was a scientific scout. It carried a magnetometer, an instrument that measures the direction and strength of magnetic fields. Pioneer's magnetometer discovered that Saturn has a strong magnetic field, and surprisingly, that its magnetic axis is almost perfectly aligned with its rotational axis. This was a puzzle, as our theories of how planets generate magnetic fields suggested there should be a tilt. The spacecraft also carried detectors for charged particles, which confirmed the existence of powerful radiation belts, though they were less intense than Jupiter's. This was critical information for planning future missions. Pioneer 11's discoveries fundamentally changed our view. It gave us our first direct measurements of Saturn's temperature, finding it to be a frigid -180 degrees Celsius. It also made the first close observations of Saturn's largest moon, Titan, revealing it to be even colder and shrouded in a thick atmosphere. The mission was a pathfinder. It proved a spacecraft could safely navigate the hazards of the outer solar system and the Saturnian environment. Its brief, fleeting glimpse provided the essential reconnaissance that would guide the next, more powerful explorers, the twin Voyager spacecraft. Following Pioneer's trail, the Voyager missions represented a monumental leap in capability. Launched in 1977, Voyager 1 arrived at Saturn on November 12, 1980, followed by its twin, Voyager 2, on August 25, 1981. These were not just flybys, they were comprehensive surveys. The Voyagers were equipped with a powerful suite of instruments, 2 television cameras, one for wide-angle views, one for narrow, detailed shots. They also carried spectrometers to analyze composition by breaking light into colors. Radio science instruments used the spacecraft's communication signal to probe atmospheres and ring structures. The images sent back by the Voyagers were breathtaking. They revealed the rings to be a stunningly complex system of thousands of individual ringlets, braids, kinks, dark spokes. The cameras discovered new, small moons hiding within and just outside the rings. Some acted as shepherd moons, their gravity sculpting the rings' sharp edges. Voyager 1's trajectory was designed to get a close look at Titan, the giant, hazy moon. The Voyager encounters revolutionized our understanding of the Saturnian moons. They transformed faint dots of light into distinct worlds. We saw the crater-pocked, ancient surface of Mimas dominated by a giant impact crater, a Death Star resemblance. We saw the two-tone surface of Iapetus, one hemisphere bright as snow, the other dark as tar. We saw grooved terrain of Enceladus, hinting at a geologically active past. Voyager's spectrometers found most moons were largely water ice, giant frozen snowballs. Voyager 1's close flyby of Titan confirmed its atmosphere was thicker than Earth's, mostly nitrogen with significant methane. Thick, orange smog obscured the surface, leaving us to wonder what lay beneath. The encounter with Titan, however, came at a cost. The gravity assist maneuver to study Titan flung Voyager 1 out of the plane of the solar system, ending its planetary tour. A year later, Voyager 2 used Saturn's gravity to catapult onward to Uranus and Neptune, continuing the grand tour. After the Voyager flybys, there was a long silence. For 2 decades, no new missions visited Saturn. But scientists and engineers were busy planning our return, not a flyby, but a long-term residency. The result? Cassini-Huygens, NASA, European Space Agency, Italian Space Agency. Launched October 15, 1997. Cassini was a school bus-sized spacecraft, the most complex interplanetary probe ever built. After a 7-year journey, it gracefully entered orbit around Saturn on July 1, 2004, beginning an unprecedented 13-year exploration of the entire Saturn system. Cassini's instrument payload was extraordinary. Its imaging science subsystem, powerful cameras, visible, ultraviolet, infrared. The visual and infrared mapping spectrometer could pierce Titan's haze and map surface features. The radar instrument mapped Titan, penetrating the thick atmosphere to reveal the hidden world beneath. Other instruments measured magnetic fields. Other instruments measured dust particles. Other instruments measured the plasma environment. Upon arrival, Cassini immediately began rewriting the textbooks. It flew directly through the gap between the F and G rings during orbital insertion. The rings were not static, but a dynamic, active environment. Images revealed towering vertical structures in the main rings, casting shadows that stretched for kilometers. It discovered tiny propeller features, wakes created by unseen moonlets embedded within the rings, giving us a glimpse into how planets might form in protoplanetary disks. It watched seasonal changes, seeing the sun illuminate the northern hemisphere and cast long shadows as the seasons turned. Cassini's long stay allowed it to become a Saturnian meteorologist. It watched the birth and evolution of a colossal storm, a great white spot that erupted in 2010. That storm eventually encircled the entire planet. It studied the mysterious hexagon at Saturn's North Pole, a 6-sided jet stream wide enough to fit 4 Earths inside. By tracking clouds and measuring wind speeds, Cassini provided a 3-dimensional view of the planet's deep, turbulent atmosphere. It also used radio occultations, passing behind the rings and passing behind the planet, to measure particle sizes, measuring particle sizes, measuring atmospheric density. Attached to the Cassini orbiter during its long journey was a passenger, the Huygens probe built by the European Space Agency. Its destiny was a one-way trip to the most mysterious moon in the solar system. On Christmas Day 2004, Cassini released the saucer-shaped probe. For 3 weeks, Huygens coasted silently toward Titan. On January 14, 2005, it plunged into the moon's thick, nitrogen-rich atmosphere at supersonic speed. Protected by a heat shield, it slowed down, deployed a series of parachutes, and began a 2.5-hour descent to a completely unknown surface. It was humanity's first and only landing in the outer solar system. During its descent, Huygens was a floating laboratory. Its instruments went to work, sampling the composition of the atmosphere at different altitudes. It measured temperature, pressure, and wind speed, finding that the winds changed direction as it got closer to the ground. A special camera, the Descent Imager Spectral Radiometer, captured hundreds of images as the probe drifted down. What it saw was astonishing. A landscape that looked eerily familiar. The images revealed drainage channels, river networks, and what appeared to be a shoreline. It was a landscape carved by liquid. When Huygens landed, it didn't crash. It thudded onto a damp, sandy plain. The impact kicked up a bit of dust, which instruments analyzed, revealing a mix of organic compounds. The surface wasn't hard rock, but had the consistency of wet sand or packed snow. The images from the ground showed a flat landscape littered with rounded pebbles, likely made of water ice, smoothed by the flow of liquid over eons. For 72 minutes, the probe transmitted data from the surface back to the orbiting Cassini, which then relayed the precious information back to Earth. It was a triumph of engineering and a monumental moment in exploration. The discoveries made by Huygens, combined with Cassini's ongoing radar mapping, painted a picture of a startlingly Earth-like world, but one operating under exotic rules. The liquid carving the rivers and filling the lakes and seas was not water. On Titan, where the surface temperature hovers around -179 degrees Celsius, water is as hard as rock. The liquid is methane and ethane, hydrocarbons that are gases on Earth, but are liquid in Titan's extreme cold. Huygens gave us our first ground truth, confirming that Titan has a weather cycle based on methane, complete with clouds, rain rivers, and seas. While Titan was a primary target, Cassini's greatest surprise came from a small, unassuming moon named Enceladus. Only 500 kilometers in diameter, this bright, icy world was thought to be a simple, frozen ball. But early in its mission, Cassini's magnetometer detected something strange as it flew past. Saturn's magnetic field was being draped and diverted around Enceladus, as if the moon had a substantial atmosphere. This was a shock. A moon this small shouldn't be able to hold on to an atmosphere. The answer came when Cassini's cameras took a closer look at the South Polar region. There, they saw something incredible. Giant plumes of icy particles and water vapor erupting from long cracks in the surface, dubbed tiger stripes. These geysers were blasting material hundreds of kilometers out into space, forming the very substance of Saturn's faint E-ring. Cassini was then directed to fly directly through these plumes. Its instruments were able to taste the spray. The cosmic dust analyzer and the ion and neutral mass spectrometer found that the plumes were composed mostly of water vapor, but they also contained salt, silica dust, and a cocktail of complex organic molecules, including methane and carbon dioxide. This discovery was a game changer. The presence of salt strongly suggested the water was coming from a liquid ocean in contact with a rocky core. The silica dust could only have formed in hot water, at least 90 degrees Celsius, implying the existence of hydrothermal vents on the floor of this hidden ocean. These are the same kinds of environments where many scientists believe life may have first started on Earth. Suddenly, this tiny moon became one of the most promising places in the solar system to search for extraterrestrial life. Enceladus had all the necessary ingredients: liquid water, organic chemistry, and a source of energy. Over the years, Cassini made 23 targeted flybys of Enceladus, each one adding more detail to the picture. Gravity measurements confirmed the existence of a global ocean hidden beneath its icy shell. The mission transformed our understanding of where life might be possible. It showed that a world doesn't need to be in the traditional habitable zone, close to its star, to have liquid water. The gravitational tug-of-war between Enceladus and Saturn generates enough tidal heat to keep its interior warm and its ocean from freezing solid. This little moon taught us to think more broadly about the habitats for life in the cosmos. After 13 years of revolutionary science, the Cassini spacecraft was running low on fuel. To avoid any chance of it one day crashing into and contaminating the potentially habitable moons of Enceladus and Titan, the mission team planned a daring final act: the grand finale. In 2017, Cassini began a series of 22 orbits through the unexplored region between Saturn and its innermost rings. It dove through this 2,400-kilometer gap again and again, sampling the planet's atmosphere, sampling the ring particles directly, and making the closest ever observations of Saturn's clouds and inner rings. This final phase was a mission in itself. The close passes allowed Cassini to precisely measure Saturn's gravity and Saturn's magnetic fields, untangling the planet's influence from that of the rings. This led to a stunning discovery. The planet's magnetic field was even more aligned with its rotation axis than previously thought, deepening the mystery of how it is generated. The data also provided an accurate measurement of the mass of the rings, which helped scientists estimate their age. The findings suggest the rings are surprisingly young, perhaps only 100 million years old, meaning they likely formed when dinosaurs still roamed the Earth. On September 15, 2017, Cassini performed its final task. It plunged into Saturn's atmosphere, fighting to keep its antenna pointed toward Earth as it transmitted its last bits of data. It became a part of the very world it had spent so long studying. The legacy of the Saturn saga, Pioneer's first hello to Cassini's final goodbye, is a treasure trove of data that will keep scientists busy for decades. We now see Saturn not as a solitary planet, but as the heart of a complex system of rings-moons, each with its own personality and secrets. We have mapped alien lakes, flown through icy geysers, and witnessed planetary weather on a colossal scale. The story does not end here. The questions raised by Cassini are now the drivers for future missions. Scientists are designing probes to return to these worlds. A mission called Dragonfly, set to launch in the coming years, will send a rotorcraft drone to fly through Titan's atmosphere and land in multiple locations, studying its prebiotic chemistry. Proposals are being developed for orbiter's landers that would return to Enceladus to analyze its plumes for biosignatures, the chemical fingerprints of life. The 50-year saga of Saturn exploration has been one of steady progress, turning a point of light into a vibrant, dynamic system of worlds, and setting the stage for the next great chapter in our search for our place in the cosmos.